Hi everyone. So now we're at this point of the day where we're actually going to be talking about prediction. So I've heard you've already had quite a journey already through all the different Hades tools. But in this part, we're going to look at whether we can predict various outcomes in the new uses of lisinopril, which you actually have already, I believe, created the phenotypes for. So what is prediction? Well, it's pretty bad to tell you what it isn't. So in OHDSI, we have three different types of analyses that we tend to work on. We have the characterization, and this answers the question of what happens to them. So you look at people who have lisinopril, and you look at what is in their history. And then you've got the population level effect estimation, and this is looking at what the causal effects are. So this is what you saw with Martine previously. And then prediction is what will happen to me. So the first is observational. It's just looking at the characteristics. The patient of prediction is the inference, and the population level effect estimation is the causal inference. So we're going to be focusing on the inference, and this effectively is going to be saying, based on my medical history, if I was to take lisinopril, what is my risk? 0 being 0 risk, 100 being I'm 100% likely of having some outcome in some future time period. So the patient of prediction framework, effectively the definition looks like this. So when you're doing prediction, you have a group of patients, which we call the target population, and this is the people you want to do the prediction for, and you have some index, some point in time where you're going to be saying, at this point in time, I want to know what would happen to them in some future time period. So target population, who you want to do the prediction for, outcome, what you want to predict, and time at risk, when you're trying to predict the outcome. So these are the components, and they're listed here. So the same as I just mentioned, basically target population is who you want to do the prediction for. Outcome, what you're predicting. Time at risk, when you're predicting. In our situation, we're looking at new users of lisinopril. So the index is the point that you actually get the drug for the first time. The outcome is the angioedema. Yeah. And then the time at risk is 1 day after the drug to 365 days. Now, you could actually have a different specification. So you could actually have said the time at risk could have been while you're on the drug, could have been the first 30 days, first 7 days. But in this case, we actually picked this as our task. So here's the same picture you saw earlier, but now you can see the T equals 0 is the first lisinopril, time at risk is 1 year, and our outcome is angioedema. So the aim of prediction is effectively to look at everything that the patients have prior to index. So the conditions, the drugs, the measurements, the procedures, and see if you can find things that are associated to the outcome. So are there things here that people have in their history that increase their risk of the outcome or decrease their risk of the outcome? So this is what we're basically doing for prediction. Now, there's lots of different design choices you make when you do a prediction. You've got to figure out how to extract your data that you're going to be learning from. You have to figure out how you're going to actually learn the model, and you've also got to figure out how you're going to fairly evaluate it. And if you actually look at lots of predictions, the way they're done, a lot of people just make choices, and they don't necessarily have reasons why, other than this is what's done. So for when you're extracting the data, there's the question of what design do you do? Do you do a cohort design? Do you do a case control design? When you're creating the features to describe people, how far back do you go? Do you look at the last 30 days? Do you look at the last 6 months, last year, any time prior? When you're doing a cohort design, you actually have an issue of sometimes you may lose people. So you may not have them observed, for example, in this case, for the full year. So if someone's only observed for 6 months, what do you do if they drop out the database and you don't know from 6 months to a year what happened to them? Do you keep them? Do you remove them? And also, how do you define your T and your O? So these are things that are going to impact the data that you're learning from. And I would say these are actually really key considerations, because if you mess up in these, you may actually make a model that isn't doing what you want and isn't generalizable. So if you're defining your target population, this is what we call the T, in an incorrect way, then you're going to have a model, but it's not actually doing what you want it to do. It's not going to be applicable to the people you want it to be applicable to. So you need to be very careful about these design choices. And I'm just going to give you a summary in the next slide about what we've learned from this. And then model development is questions like, do you pre-process the data? how basically do we manipulate the data we have in a way that can help us to fit a model? Also, what model to fit? So do you do a logistic regression? Do you do a gradient boosted machine? Deep learning? These are all questions that there's no clear choice. And then when you're fitting a model, there are some things that you should probably look at, like diagnostics. Do you have enough outcomes? Is your database suitable for what you're trying to predict? And again, these haven't always been looked into when people have done prediction models. If you look at a lot of published models, there's probably issues in many of these choices that people have made, and it's just not really even considered. Validation, when you apply the model, you want to try and figure out how well the model will do in new data. So you need to have an appropriate way to validate a model. And you also need to make sure that the metrics that you're reporting are useful for people. If you actually use different metrics to the standard, it's going to be hard to compare across models. So we've actually been working a lot in OHDSI to come up with answers to all of these questions. So the first thing we asked you to do a cohort case control design. We've actually shown that you should do a cohort design. If you do a case control design, you're going to end up with calibration issues, almost certainly, because you're overestimating you're overrepresenting the outcome patients in your data. And that basically is going to cause calibration unless you do some refitting. You also have to be careful if you do inclusion-exclusion criteria, you may actually be causing a bias. And we did a study that actually showed that if you remove people who don't have the outcome and lost the follow-up, but you keep people who had the outcome before they lost the follow-up, you can actually cause a real big bias in your models. Covariate look-back, we actually researched this, and we found that really, if you keep it too short, you're probably going to have some issues in the predictability of your model. So if you only use, say, the last 7 days, you may not get as good a model if you look back a whole year to create your features. So we've been looking at all these at scale and investigating these impacts. And what you actually see, and for model development, we've been looking at things like, should you oversample, undersample to balance the people with the outcome and non-outcome? Is there one classifier that's better, or should you try everything? So we've been looking at all of these questions and all of these best practices. And the good news is that the PLP framework actually forces you to do the correct best practice from what we've learned so far. So PLP by design uses a cohort design. So the bits in red basically are the things that PLP is enforcing that you do that is based on the research that we've done has shown that what you should be doing. So the red bits are the things that PLP is making sure that you do correctly. The bits that are in bold and blue, these are things that PLP helps you do. So you should be doing, if you use PLP, you can make sure that you do the best practice, but you still need to make sure you're making the right choices. I'll be showing you how you can actually make sure you pick the right choices for these. The bits that isn't highlighted you'll see is the phenotype, the T and the O. PLP won't tell you if your T and your O is correct, but fortunately you've seen from other tools in Hades, we can actually look into that. So you did the cohort diagnostics to see if your T and your O was correct, and you've actually done a lot of work already for that. So this is the part outside of PLP that you need to make sure is correct. And if you don't have the correct target population or the correct outcome, as I mentioned, your model is not going to be doing what you want. It won't be necessarily applicable to the people you want to apply it to. So you do need to spend a lot of time making sure your target and your outcome cohorts are correct. So let's see this in action. So in the components that we have, the task, we are looking at the new users of lisinopril. So that's our target cohort, looking at angioedema as our outcome, and the time at risk is 1 day to 365 days after the lisinopril. That got cut out of this table. So what we chose is for the model, as I mentioned, you may not want to just do one type of model. So you could actually do a logistic regression, a gradient boosted machine, and a random forest, see which ones does the best. But I'm going to be showing you the lasso logistic regression just because that one is nice to explore. But that's the best practice, just do them all. We have a framework that lets you do everything. Covariates, we're looking at some demographics, and we're also looking at things like conditions, drugs, procedures, measurements that occurred in the 1 year prior to index. As you mentioned, that was guided again from best practices. We've done research to show that you don't want to look in kind of like a short look back. You actually want to have something a bit more longer, like a year as your look back. And then we use the Pharmatrix database. But we actually probably want to check to make sure the diagnostics are good in that database before we overinterpret the model. So let's actually explore this. So unfortunately, I wasn't able to predict that I don't know how to use my Mac. But maybe in the future I will be able to. So let me zoom in on this. So we basically have a Shiny app for viewing the results. So I basically used the tools that we have in OHDSI to create the models, and I actually thought it's more fun to explore the results. So that's why I wanted to kind of jump to the models, and I'll show you the design choices we made. It's all stored in this Shiny app. So the Shiny app for PLP looks like this. It has a nice little introduction to begin with, but the more exciting page is this prediction tab. So if you go over to the prediction tab, and I just want to ask people not to use this link on the Shiny app for now, just so it doesn't crash while I'm presenting it. But you will have a link after I've played around with this, and you can have a play with it as well. So we have 2 rows here for 2 different models that I fit. So the first one is the new users of lisinopril and the angioedema events. That is why that has an issue with Shiny if there's lots of people. But hopefully it won't crash again. So basically this is the outcome that I was just saying for our prediction task. And then the viewer is design-centric. So each row corresponds to a design. So a target population, an outcome, a time at risk, and all the different settings, so the covariate settings and any sort of pre-processing settings you want to do. So anything that differs in those settings will have a different row. So we just have one model design for our task of angioedema prediction and one model design for our tasks of acute myocardial infarction prediction. And then these columns here will tell you how many databases have been used to develop a model or validate a model. So in this case, we just have one. But the framework we have, you can actually do things at scale pretty easily. So I could have actually done this model across lots of databases. I could have given the model to other people for them to apply to their databases or develop on their databases. So actually with the OHDSI framework, we could have actually got this much higher than one. But for illustration, you probably just want to have one to play around with it. And then you have a summary. So if you have lots of different databases, you can actually see how well the model performs in terms of discrimination. The minimum, the mean, and the max across all the different data sets. So here you can see actually angioedema, this is the test performance. So you have a holdout set when you do the validation. When you fit the model, you fit in a subset of the data set, and you hold some data out to actually see how well the model does. And that's what's used for this AUC here. So we have a 0.63, which isn't the best, but you're getting some predictability. And then you can see here our time at risk was 1 day to 365 days from the start of the drug. So there's 3 buttons here which you can click. The first one is the diagnostics. So this is something that was newly added this year to PLP. And in here, for every database that you've run the diagnostics on, it will give you information about whether you've passed the diagnostics. So we only ran it on 1 data set, but we can see whether there's any issues flagged in the model design for that database. So you can just look across and you can see pass, 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 that's good. You want to see that. Unknown means there's probably something you need to check. And then unknown here, this 4.1 is basically saying that we may not have enough outcomes for our model to be fit and for us to be confident about how well it's going to do. You can also look at, there's this button that tells you the outcome survival. So this is basically telling you when the outcome occurred. So you can see that there's actually kind of like a quick kind of like decrease here, which is saying that actually the outcome was more common. So the angioedema actually occurred quite close to index, so quite close to the start of the drug, and then kind of slowed down. So this is kind of interesting. I use this to explore to see if I have the correct time at risk. If this was still rapidly decreasing, maybe you want to have a longer time at risk, and this can actually just help guide whether your time at risk was correct. But a 1 year time at risk seems to be something that we still want to explore. So then once you're happy with the diagnostics, as I mentioned, there may be something problematic because we did see that there was something we need to check. You can actually go to this view models. So the view model now will actually show you the model that was trained in pharmetrics for this task of interest. And you'll see here a column here tells you logistics. So this tells you we fit a logistic regression. time at risk is repeated again, it's 1 year. You see the AUC of 0.63, as I mentioned, this is for the test set, and this isn't the best performance, but it means that we've got some ability to discriminate between who gets the outcome and who doesn't. You have other metrics that can be useful. So error under precision recall curve. This is a metric that's useful if your outcome is rare. You'll see your AUC is going to be low, even if your error under precision recall curve can be low, even if your error under curve is high. And that basically is saying that you're getting you're ranking well, but because your outcome's so rare, you've basically got a high false positive rate, and it's going to be problematic. So this is a good thing to look at because it's going to tell you if you've got some issue of like model rareness, it's probably going to make it so that your model is not going to be that useful. And we see this here because the outcome is pretty rare. Our error under precision recall curve isn't that great. So this model isn't actually fantastic, but this is the model I'm showing, and the model you're looking at hopefully will be a bit better. So the T size is the number of people that you are developing the model on. Your O count is how many of these people had the outcome. And we actually saw the diagnostics. The reason that it said it was unknown whether you pass the diagnostics is because this count isn't great. Ideally, in the research that Henrik's done at Erasmus University, he actually showed that the model performance gets better as you get more outcomes, but it kind of gets to a point where adding more outcomes doesn't help. And he found that really it doesn't seem to level off, I think, until around 2,000 to 3,000 outcomes. And looking at it, you really want to try and get about 1,000 outcomes if you fit a model. So ideally, when you're fitting a model, if you have 1,000 outcomes or more, that's great. If you have less than 1,000 outcomes, then you may actually have problems. So that's why the diagnostics failed, or didn't really fail, because it will fail if it's less than 100. But between 100 and 1,000, it's basically going to come out a question mark and say maybe you don't have enough data for this model in this database. So if we click on the results, it will actually then let us see all of the designs that we had for this prediction model. So I can look at the attrition, which isn't really a design, but it tells you how many people we lost or how much data we had to fit the model. And we can see different inclusion-exclusion criteria that we applied, and we can see if it actually dropped anyone. So here we lost some people when we said they couldn't have the outcome prior. And we also removed some people who basically left the database at index. So they had no observations, so they got excluded. You can see how many outcomes you have, and you can see how that drops down as well with your inclusion and exclusion. So attrition is a nice one to look at just to see what was the impact of my choices of inclusion. In this bit, you can also look at your covariates. So you can see what covariate choices you made. So if I click here, it will tell me which covariates I included. Extend this a bit more. So true means that I actually have this included. False means that I didn't have it. So I included gender, age groups, race, ethnicity, condition group long-term, drug group long-term, procedure long-term, device long-term, measurement long-term, observation long-term. So long-term is looking back 1 year, and I included pretty much everything. I also had the visit concept count long-term, so how many visits they had in the last year for different types of visits. And that was the feature set. So this probably would have created tens of thousands of features that would have actually candidate predictors that went into the model. And if I order by this one, I believe, this tells me as well if I want to look at what was my long-term start date is minus 365. So if you didn't believe me that I used 1 year back, you could look here and it says that you actually went back minus 365 days prior to index, and we included the day of index. And then you can actually look at your population settings as well to make sure that I followed best practices. So here it's saying that I okay. So the required time at risk is the one that can cause bias. If you pick this one and you then include all outcomes, you basically could have problems. You can see here I set this to false. So I didn't basically exclude people if they were lost to follow-up. And that's because best practice, we showed that you don't want to have this to true and this to true. If you have both of those as true, you're going to have problems with your model. So you can explore everything that you've picked for your model, but the more fun thing to look at is what is my model? So what things actually were associated to having the angioedemia? Here we basically had 20 variables selected. We fit a logistic regression, so you'll see like the intercept. So this actually page here tells you the model. You could actually apply this model to your data using this information here. There's easier ways to apply a model with our framework, but if you really wanted to, you could actually recreate the model from this slide here. So you got the intercept, and we actually have all the coefficients for the covariates that were included in the model as well. So we can order by value, which will give you the variables that were most associated for logistic regression. And for other models, it will tell you the things that basically were the most important in the model. So we can see here what predictors, which seems to be hormones, were most predictive of having the angioedema. And then you can also look at things like how often it occurred in people with the outcome and how often it occurred in people without the outcome. So this is saying this drug group occurred in 16% of the people who had the outcome, but only 3.5% of the people who didn't have the outcome. So you can see that there's actually quite a difference. This is much more common in people who had the outcome. If you don't want to order by the model value, you can also order by standardized mean difference, which is just looking at how big is the difference between the outcome mean and the non-outcome mean. So if we order by that, we can actually see it's the same thing, I believe. So you can look through and see what things popped up and how associated were they. So this is kind of if you just want to look into your model. Although we do have a paper that says you shouldn't use prediction for risk factors, so you don't want to overinterpret this. Threshold summary gives you your information like your sensitivity, specificity, PPV of your model for lots of different thresholds. So this is more if you wanted to apply this model clinically, you could actually move this across to find a point where your PPV and your sensitivity and your specificity is something that you want. And when you move this, you actually see this all changes. So as you move this down, the PPV will decrease, but the sensitivity should increase. If you move this up, the PPV will increase and the sensitivity decrease. So normally when you apply a model, there's going to be a sensitivity and a PPV that you want to have. You can actually figure out what the threshold you should be using to apply the model will be based on these. Discrimination is the most commonly recorded or presented metric for prediction. It basically tells you how well the model's ranking. Is it given the higher risk to people who are going to have the outcome and the lower risk to people who aren't going to have the outcome? You can have a look at this on this view. So we have 3 different evaluations. We have the test, the train, and the cross-validation. So the test is the performance of discrimination performance in the held out data. The train is the discrimination performance in the data that's used to fit the model. And the cross-validation is the performance when you're basically using the trained data but holding out some data each time. So this is kind of its own kind of like hold out within the train. And the AUC, as I mentioned, 0.5 is random. Your model is not able to predict. 1 is perfect. We're not getting the greatest performance here. But what is interesting to look in this is to look at the difference between the train and the test. So here we're actually getting a 0.67 in the train and a 0.63 in the test, which is actually quite different. And this is actually going to indicate something called as overfitting. So in this, our model overfit because the train is much higher than the test. So if you see overfitting, actually, you may want to revise your model design. You may want to change the covariates, maybe reduce the number of covariates. You may want to try a different model, try different hyperparameters, because if you can prevent the overfitting, you might actually be able to get better on the test set. But if we look into this, so ignoring that, if we look into, we can actually see the plots as well. So you get the standard ROC plot that most people will present in a prediction. We also have the precision recall plot. As I mentioned, this is an interesting view if your outcome's rare. And for us, actually, the outcome was pretty rare, so this may be something you want to focus more on because it shows you have this like high false positive rate issue. And then we can also see the predicted risks in the people who had the outcome versus the people who didn't as box plots, and it just shows you how separated they are by the model. The more these are separated, the better your model. Our model had an AUC of 0.6, it wasn't great, so these aren't going to be that separated. And then we have this view basically as another few more perspectives, but effectively it's these 3 things are showing the same. How separated are the people who have the outcome and the people who don't with your model. Calibration is a metric that's often ignored by people in the literature, but it's actually very important. So calibration isn't about ranking. Calibration is, if I say you have a 10% risk, do you really have a 10% risk? So when you do a prediction model, you do want to make sure if you're going to be applying it, it's well calibrated. If we look at the test calibration, the nicest plot is this plot here. If your model is well calibrated, the dots should fall on this diagonal, this red dash. We're not getting that, so this model isn't the most calibrated. So we definitely have calibration issues, and this is something to be aware of. If you're applying this clinically, you need to kind of like let people know this calibration is not great, and you should probably fix this if you are going to be applying this. So this is one example of a model, but you all actually now can play around with the next model. So if you head to data.odyssey, if you can do this maybe in your tables. So as a table, if one of you wants to load this up and then play around, we have a bunch of these Odyssey prediction tutorial links. So I'm going to give you each table a number.
Yeah, you go for it. Yeah, you got it.
Oh, do you want it?
Well, I was just going to get everybody to. You guys are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Did I get ready? And 14 back there for the next one.
So if you can all go to Odyssey prediction tutorial and then your number, you'll be able to load up the Shiny app and then play around. And we have some questions to see if you remember how to use the Shiny.
Always trust your one's a rock.
Number 1.
Okay, so these are some tasks to see if you can play around and with the myocardial infarction, see if you can actually answer these 8 questions.
So this is just a general question. So with all of the covariates that are being used and comparing multiple models and things, where are we adjusting for that, for multiple comparisons and things? Is it baked in? Is that something that happens after this workflow? Where are we doing that?
So with prediction, your aim is just to kind of come up with a model that predicts the best that it can. The issue with throwing all the model variables in that can happen with PLP is you can overfit, and that's what we actually saw happen because we only had like 300 outcomes, but we're putting in a lot of covariates. You kind of open yourself up to this overfitting. So what we've done to address that is we have something called regularization in our models, which effectively does feature selection when it's fitting the model. And so effectively it penalizes a very complex model. So it will, if you had a model that had 10,000 features, and it performed the same as a model that had 200 features, it's going to say use the 200 feature model. So we have that built in to try and stop the overfitting. But unlike causal inference, because we're just aiming to optimize prediction, we don't really care if it's confounding. We just want to maximize the prediction and minimize the complexity of the model.
Okay, thank you.
Okay, so I had some time to play with the Shiny app, and if you have any feedback with the Shiny app, please let me know. I understand it probably would have crashed if there was multiple people using it, so I do know about that issue. But any other issues, let me know if you have any user feedback. I'm always trying to make it a little bit more friendly, so any questions you have, I'm sure other people would have had, well, any issues you've had, other people are going to have the same issues. So to run through these questions, I'm just going to go back to the Shiny app so I can actually show you where I think it is, as long as the screen sharing works. There we go. So it was in here.
Oh, that's good.
Okay, so the first question, how many outcomes used to train the model? Does anyone have any answers for this? Do you know how many outcomes we had when we were fitting this model? Sorry, 100? 470. Let's have a look. 471? Okay, so we go to the view models, and you go across, and it is 471. Yeah, nice. And then the second question is, what look back was used for the covariates? So this one was a little bit of a sneaky one, actually. This one may have been a bit harder to find. Does anyone know what look back we used for the covariates for this?
Yes, 2 years.
Oh, nice. Yeah, that was, yeah. So in that one, if you go to the view results, if you go to the covariates view, and then you go to the settings, you can see that the long-term start date was 730. So, yeah, that was really, I wasn't expecting anyone to get that. Okay, so sorry, my phone's gone to sleep with the questions. So the third question was, did the model design pass diagnostics? So what did people think for this? Pass or fail? So this one was another tricky one, so or a sneaky one. So if we go to the diagnostics, so one feedback I'm sure that you're going to say is, what does 1.1 and 1.2 mean? That's going to be added in the near future, so there will be a hover that tells you that. So effectively there was nothing that failed in this diagnostics. The only thing was this unknown and this unknown. So there's a few things that you may want to check into. The unknown, this 4.1 is basically how many outcomes, and we saw those 471. So I would say that's still quite a lot of outcomes used to fit the model. So I would say, yeah, this is probably passed. We do need to make this more objective, though, based on the presentation that Patrick was doing on Friday, to make sure that diagnostics aren't subjective. Unknown isn't really the best. So this is going to be some research into developing this a little bit more. So the fourth question was, what type of model was developed? Does anyone know what type of model Yeah, okay, nice. So that one, again, if you go to the view models, you'll see the model type here. We've got the fit XGBoost here. So this is the XGBoost. Again, my own kind of criticism, I would say this isn't the most intuitive. So I'm glad that people actually figure this out, because this should have a nicer name. So I will have that as a nicer name at some point. So next question. Sorry, I had to take a screenshot of all the questions. How are we doing on time?
Good.
Okay, so fifth question was, what were the top 5 predictors? So this one might be hard to shout out, but does anyone know what was the process that was used to identify the top 5 predictors? Or maybe just, what was the top predictor? Heart disease. Okay, let me just check. Just got to reload. Okay, so seems the Shiny app isn't too responsive right now. But effectively, the way you'd go is you'd go to the model, and if you go to the, oh, here we go, it's loading up now. So if you go to the model design, and we say view models, so normally you'd go to the view models, and then within the models, you could basically go to the model tab, and then the model tab will have that plot and the table. So something is off with our server right now, I think. Yeah, there we go.
Just swipe a credit card.
So here we go. So we go to the models, and then we go to the view results, and then to the model tab again. So we really like the model tab here. And then if you go to the model table, it will actually give you a list of all the variables that we're in. So this time we had 355, so it was a lot more than the angioedema. And if you order by value, you'll see that the top one is heart disease, so correct again. And then question number 6, what was the AUROC for the train, test, and cross-validations? Did the model overfit? What did... Did it overfit?
Yes.
Okay, so to look at that one, you go to the discrimination tab, and then you can see here the test, train, cross-validation, the performances, and you can actually see there is a big jump. So I actually wrote these questions without even looking at this results, and actually, yeah, this is actually really highlighting that there is an overfitting issue going on here. So we may be able to get a better model if we could address this overfitting.
So Jenna, I did have a few people ask how exactly did you address that overfitting? Can you just give a view of how you do that?
Yeah, so a lot of the times the overfitting happens because we're doing this data-driven approach where we're putting all these covariates in. we're basically making it so the model can be very complex because it's got very high dimensionality. So one way to address overfitting is to just reduce the number of covariates you'd put in. So the candidate covariates. So we put in all procedures, measurements, observations. We threw everything in there. But if you just said maybe just conditions and demographics, you might do better. And maybe actually when the phenotype library is fully available, we could actually have phenotypes as features. And again, that could give you fewer covariates that may actually still be pretty predictive.
Can you remind us what is the difference between train and CV there?
Yeah, so that's a great question. So train is, well, actually, so let me go to cross-validation. So cross-validation, when we're trying to fit a model, you have some things called hyperparameters that effectively tell you how complex the model can be. And you have to fit that depending on your data. So sometimes you may have a prediction task that's easy, so you don't need as complex a model. Sometimes you may have a very complex model, very complex task that needs a very complex model. So you do cross-validation to pick the hyperparameters in a fair way. So cross-validation is, say you have a whole data set. If you do a threefold cross-validation, which is the default in PLP, you would split your training data into 3 different groups. And you would fit the model for the hyperparameter settings you're interested in 2 thirds, so 2 of those groups, and you would apply it to the third group. So the third group, basically, the fold is its own holdout. And you do that for every combination of those 3. So you take 2 of the 3, fit the model, apply it to the third 3 times to basically see how well the hyperparameter is doing. And then you pick the best hyperparameters settings based on that. And then you fit the final model in the training data using all of the data, so all of those 3 groups. And that will then give you your final model, and then that applied to itself gives you the train. So it's not a holdout. So the train is basically, this is how the model did on the people used to fit it. So it's not fair because it's seen the data, it's fit for these people. The test is you have another group that you didn't use for your training at all, and didn't use for your hyperparameter, which is completely held out. And the model then that's fit on this training data, then gets applied based on the hyperparameters that were chosen on the cross-validation, gets applied to the test set. And this gives you a fair evaluation. It's like these people in the test set were completely held out. I'm just looking at, did the model's predictions match the ground truth? So the test set is what I would mostly look at if I'm inspecting a model. I'm looking at the test AUC. If you've got a small data set, then your test set may be really small and the number of outcomes may be really small. And then you've got this issue of your confidence intervals, these things here, are going to be very wide, and you might not be able to get much insight from the test. So in that case, I might go to the cross-validation because it's bigger, and you still had this holdout. So I may look at that. So in general, I just focus on this unless the data's small, and then maybe you go to cross-validation.
So Jenna, a naive question maybe, but so if you used a single data set for this model, obviously you could use a number of data sets in a federated approach and so on, but what determines the rule or the criteria for the size of different data sets, like the test data set? And is that set within the model and the application? Or can you actually adjust that? I mean, what's the determining criteria?
So that's an excellent question. So default in PLP is to use 25% of the data for the test set to hold out. And then you use the rest to do the model fitting, and it has threefold cross-validation. So that's the default if you don't pick anything. But really, you should be looking at your data size and figuring out what is the best design. So if you have big data, it's not really going to matter. If you have a lot of data, you can have whatever, like you could have a 25%, 20% test set and use the rest to do the model fitting. So you're kind of quite fortunate. If you had really big, you could actually just have a 50-50 test and train. It comes more of an issue if you have small data. How do you pick this design? And if you have really tiny data, you probably shouldn't be doing a test train cross-validation. You should probably be doing bootstrap, and that's what people have kind of found in the research. So yeah, basically this is we did some research that if you have big data, it doesn't really matter how you do it as long as you have some holdout, and you basically you probably just do a 25%. If you have small data, our framework really isn't made optimized for the small data. So in that situation, you might want to do some bootstrapping and not use this framework.
So So like, for instance, in a use case of like rare diseases or where you've got small numbers of registries, for instance, so for very limited data sets, that's where you're going to run into more of those challenges.
Yeah, so if you've got small data, our PLP framework is made for big data. If you've got small data, you will have this. We have got it so you can actually customize this, and there is a way of actually changing this, but you would have to do your own code for it. So we try to make it adaptable for smaller data, but it's not made for small data, unfortunately.
Thank you.
Okay, so 1 more minute. So we've got was the model well calibrated? Any thoughts on was the model well calibrated?
But you got to that.
So the calibration, if you go to this plot, again, I tend to look at the test, especially because we had 400 outcomes. So in the test, there was about 100, which is a decent amount for the validation. You can see the plot. So it's just plotting it now, very slowly. But effectively, if the model is well calibrated, we should see the dots fall on the diagonal. If it's not on the diagonal, then you've got some calibration. I would say this is not the best calibrated. We are seeing kind of some dots out here that are pretty bad. So we're actually seeing in this region, so for the lower risk, we're seeing a higher observed risk than predicted. So we're actually underestimating risk in this area. And then here we're seeing a lower observed risk than predicted. So we're actually underestimating risk here. So overestimating risk here. So we're actually not that great in calibration. So this would be something that you'd pretty want to be wary of. If you wanted a model you could apply clinically, this is kind of worrisome. You may have to do some adjustment to fix the calibration. Time. Okay, so the next thing was just the attrition, which was basically go to design settings, and you can view the attrition here. This is sometimes impacted by the cohort. So if your phenotype has different settings, for example, if you already said they have to have 365 days per observation, then you're not going to see it here because this is what happens once you've extracted the data from using the phenotype. But yeah, I hope everyone had fun playing with the app. And like I said, if you have any feedback for this, or if you have any questions on prediction, we're going to be having prediction work groups monthly. So if you want to get more involved in prediction, look out for an email. We'll probably be advertising it on the Tuesday call as well. But, thanks.